This is the AP review session that goes over Chapter 8 and 9. And this deals with molecular drawings and polarity and molecular forces eventually. So we'll take a look at both of these. In this first video, we'll focus more on Lewis structures. So I'm going to go through a bunch of these quickly. And the first question says, which has two lone pairs of electrons? Remember, we have to learn how to draw Lewis structures of these. So the way we learn how to draw Lewis structures is if we take a look at water, simple example, we first total up the number of valence electrons. So we take oxygen brings, remember, 6 valence electrons, and you should be able to spot these from the periodic table. These are the S valence electrons, are the S and the P electrons of the same energy level. So oxygen brings 6, hydrogen brings 1 each, so we have 1 plus 1. We have a total of 8 valence electrons. So oxygen gets 2 hydrogens around it. That is how we begin with the molecule. This one's pretty easy because we have 1, 2, 3, 4. Remember, each line represents 2 electrons. 5, 6, 7, 8. So actually, you got yourself water as having 2 lone pairs of electrons. So 2 lone pairs, meaning this one and this one here. Incidentally, NH3 will have 1 lone pair, and CH4 will have no lone pairs. CH4 will be completely filled with electrons. This is because the octet rule is usually followed by elements. Octet rule meaning you have yourself 8 electrons around each element. Remember, hydrogen only needs 2. Number 2 actually shows one of the exceptions. Here it says, which has a central atom with less than an octet. Now, if you take a look at BH3 and you total up BH3's valence electrons, it's impossible to get 8 because boron only brings 3 valence electrons. So we got 3 from all the hydrogens. You only get 6. So in this case, BH3 will exhibit less than an octet, and it will look like this. And it will actually be trigonal planar for its structure, which we'll take a look at in a second. Now, number 3 says resonance is most commonly used to describe the bonding in molecules of which the following. Now, remember, resonance is where you have double bonds, and those double bonds could be in different places, different equivalent places. So let me quickly go through the one that is the answer. This will actually be O3, which is ozone. If you total up, each oxygen brings 6 times 3, you get 18 valence electrons. So you have 3 oxygens essentially around each other. If you have 18 valence electrons, you got 2, 4. But first put them around the outside, remember, and then anything extra put on the inside. So you have 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 2 more to put on the central atom. Oxygen is a little deficient, a little upset. The oxygen on the right says, no worries. We will share my electrons with you. This does not increase oxygen's valence electrons. They just get pulled onto the inside. So this is the correct structure. Now, the double bond could have just as easily been on the right side, and in fact, it is on the right side. So the electrons can switch, and this oxygen, you can say, will share. So that's how we draw, remember, the double arrow indicating resonance, and now we show the double bond on the right side with this oxygen having 2 lone pairs. And this would be resonance. You want to still ensure that each element has 8 valence electrons. So in this case, this is 8, 2, 4, 6, 8. This is 8, 2, 4, 6, 8, 2, 4, 6, 8. And that should work. So oxygen, ozone has resonance. None of the rest have resonance. Now CO2, if you recall, CO2 actually has 2 double bonds to the left and to the right. And it looks like this. So it doesn't have resonance because these are equal, essentially equivalent. Good. Now, number 4 says, which of the following compounds is least likely to exist? And the answer is NF5, right? This one right here. NF5 is least likely to exist. It turns out that phosphorus, as well as antimony, are lower in the periodic table, beyond row 3 or energy level 3, which means they can actually have more than an octet. They can have 10, maybe even 12 valence electrons around them. But nitrogen, being in the second period, take a look at nitrogen. Nitrogen is actually right here. If you recall, we just had this discussion right after carbon and before oxygen. Nitrogen is in the second shell, so it does not have access to its 3D subshell. So no, nitrogen has no D subshell, which means it can't accommodate more than just 8, because 8 comes from 2s, 6p. So you get 8. You cannot have more than 8 for nitrogen. So this one exists, this one does not exist. All right, how about we take a look at number 5. Let's clean this up a bit. So we have which is predicted to have the largest bond angle. Now when we draw these molecules, we can see their bond angles. If we draw CH4, for example, remember the most famous bond angle is 109.5 degrees. This is for tetrahedral molecules, where you have 4 atoms around the outside. And so we have 3 here that will display bond angles close to 109.5. NH3 being very similar except with a lone pair on top will also be 109.5, but each one of these will be a little less than 109.5. This is because the lone pair of electrons exhibits more repulsive force, pushing these lower and tightening this angle up a little bit. The same thing happens with water, except with a stronger effect. These 2 lone pairs, now remember water is really drawn like this. In 3 dimensions, water is bent. So you have these lone pairs of electrons that really exhibit repulsive forces pulling this together, and it's really, really less than 109.5. So degrees. So that's why water will actually have the lowest, all right, which means the largest bond angle. Well, the bond angle between atoms or, good question. So that would put CH4, oh wait a minute, no, BH3, aha. So I was answering the question backwards. So water has the smallest bond angle, excellent. BH3, remember BH3, this is good old not following the octet rule, which means it has trigonal planar arrangement, trigonal planar gives you 120 full degrees. Very nice. So BH3 is the correct answer. Now, you also have trigonal pyramidal, which is up here, but recall the other angle could be from a triple bond and a single bond, or 2 double bonds, and this would be 180. This would be the other angle. So really, you're usually worried about 3 angles. 109.5, which is the most common, 120, which is between trigonal planar, and 180, which is between linear. I think we'll see this one in just a moment here. So let's take a look at number 7. Well, let's do number 6. This actually talks a little bit about geometry. So trigonal pyramidal represents the fact that you have 3 atoms, but then you have an extra electron pair, which pushes down, and you get trigonal pyramidal. So this one will actually look more like this. Here's the nitrogen, and here are your hydrogens, lone pair. So this is trigonal pyramidal right here. This would be tetrahedral. This would be bent. Recall, this is trigonal planar, and this would be linear. So say if this was nitrogen, this was hydrogen, something like that, this would be linear. Now you do have higher order structures as well. Those are more rare, but there is a few questions down below where you have trigonal bipyramidal. This is with 5 electron domains, and it's getting a bit crowded, which can come down into, remember, T-shaped and seesaw. So seesaw and T-shaped. I should really be doing this on a separate sheet. And you also have octahedral, which comes down into square pyramidal, and then square planar. So review those, take a look at your previous notes to get those, but your trigonal pyramidal, in this case, then would be NH3. All right, let's clean this up a bit, and take a look at number 7. Number 7 says, which of the following molecule contains exactly 3 sigma bonds and 2 pi bonds? Now, sigma and pi bonds, sigma bonds are single bonds, and pi bonds are double and triple bonds. So we need, or really, so multiple bonds, because a double bond could be a pi, and a triple bond can be a pi. The pi bonds, recall, are the ones that are above and below. The sigma is the one that's right between the two nuclei. So this is sigma, and your pi is above and below. Because above and below, this is from orbitals that have not been hybridized, which we'll take a look at in a second. So in this case, we have ourselves, if you take a look at the molecule, this one right here. Watch, take a look at C2H2. If you draw its structure correctly, I want you to try to pause and draw the structure. You will actually see that you have 2 carbons, wait a minute, 3 sigma and 2 pi's. This one will actually look like this if you draw the structure, which gives you sigma bonds are single bonds. So here's a sigma, 1, 2, 3, these are sigma. And your pi bonds then are right here. These are pi. So it's 3 sigma, 2 pi, give us this. Good? Well, let me actually talk about hybridization with number 10. So take a look at number 10. This deals with Sp2 hybridization. Now hybridization is, remember, whenever we form these bonds, so if we have CH4, for example, which is one of the answers right here, what you do is you have to collect 3 equivalent bonds. So here we have 3 bonds. And then you have to hybridize them, and your choices are, you have an s orbital, you have 3 p orbitals, you have 5 d orbitals. So since you need 4 equivalent bonds, what you would need to do is you would need to take the first 4, so 1, 2, 3, 4. This would give you sp3 hybrid orbitals. So it's actually pretty simple, and what we need to do is we need to find sp2. Now sp2 hybridization famously has double bonds, because if you have a double bond right here, to get sp2 you need 3 equivalents. You have 1, 2, 3 areas of electrons, so you need an s and 2 p. So this would actually be consistent with this structure right here. If you draw this structure out, once you go ahead and pause and try to draw it out, what you'll see is there are 2 carbons, 2 hydrogens, and 2 chlorines, like this. You say this is a chlorine, which requires carbon to have a double bond. So in fact, you have 3 areas of electrons that have to be hybridized around the carbon, and so these 3 have to be equivalent. So it has to take 3 orbitals, and it does so by just taking these 2, and you get sp2, just like it asks for. Now the last bond right here is an unhybridized orbital. That unhybridized orbital is what the pi bond is all about. It stays above and below. It never participates in the bonding between the elements. It stays above and below. And the same thing happens to the next one, and then that's how your pi bond is created. That's a lot of information very quickly. Take a look at our regular notes to kind of wrap up that concept. Let me finish up then with number 8, because these chapters also talk about polarity. Remember, polarity is the difference between the 2 elements' electronegativity. So you can have a polar bond, but a nonpolar molecule, and that's what it's asking about here. Polar bonds, but nonpolar molecule. That will be true in CCl4. This is a nonpolar molecule because it is equally distributed. All the chlorines are equally distributed in the tetrahedral fashion. All the electrons are pulled away with the same strength. But each of these is actually a polar bond. In fact, the electrons are pulled this way toward the chlorine because chlorine has a higher electronegativity. It wants electrons more. Chlorine is the 4th most electronegative element on the periodic table. So each one of these is actually electronegative, and this is one of the ways to express electronegativity. The electrons go toward the head of the arrow, so they go toward the chlorine, but because it's a symmetrical molecule, you got symmetry here, all of them cancel out, and overall it has no polarity. And we measure polarity by something called dipole moment. Dipole moment equals 0. All right, that was quick. I explained each one of these very quickly and probably somewhat confusingly. I hope this is an easier concept to recall, to remember. Work through the rest of the questions, and then we'll take a look at a bunch in class.